Okay, so now our next area of study is going to be the idea of magnetism, and we're going to just first study magnetism kind of by itself and then look at how charges and how electricity relates to magnetism in the field of electromagnetism. So, first big question is, where does magnetism innately come from? And it comes from a property of the electron called spin. And this property of spin actually causes the electron to act like a tiny magnet. And so every electron, just in its innate little movement, is going to have this tiny kind of magnetic field associated with it. Most time, the electron by itself, you're not going to even really notice it. But it is kind of why when you look at when electrons pair up in the valence shells and you have these two electrons pair up, you always have a spin up and then a spin down pairing up each other.
Okay, so this model is our classic model of the hydrogen atom. You've got the proton and the neutron, you've got the electron path. And this is the simplified model where we just have the electron and it's like orbiting circularly around the nucleus. But in reality, we don't really know exactly where it is. We have statistical analysis of the most probable place where the electron is going to be. But really, they're just kind of like zipping all over the place is the actual physical reality of this. Now, when we have two electrons that are paired together in their orbital, their spins are in the opposite direction. And so you can see that rotation is opposite. So one is a spin up electron and one is a spin down electron. And they each have their own individual magnetic moment, but the net magnetic moment for that orbital is zero because they're effectively canceling each other out.
So that's innately where you get magnetism from. Now there are certain materials that tend to be what we call the ferromagnetic materials. And ferromagnetic materials, they are iron, cobalt, and nickel. And with these materials, what happens is in these particular atoms, when you have this metallic bonding of these atoms, you end up having these regions of these atoms where their spins of, like all the electrons, all these unpaired electrons, their spins happen to be going in the same direction. So I'm going to show you a picture of that. Kind of wait for this little thing to go by. So what happens is in a ferromagnetic material, you have these regions called domains. And these regions of domains are where you have these unpaired electrons whose spins are all in the same direction. And so it's like you've got a tiny little magnetic field that's all going in that same direction right here in this domain. And then in this domain, you have another tiny magnetic field that's pointing in the same direction. And so you end up having these regions of unpaired electrons whose spins are all happening to be in the same direction. So that's just innately if you have iron, cobalt, or nickel. They have these tiny magnetic fields within them, but they're not lined up to actually create a strong enough magnetic field that you could actually notice it. But if you take one of those magnetic materials and you put it in an external magnetic field, when you put it in an external magnetic field, all the spins will line up with that magnetic field, and then you can get all the domains to have their magnetic fields pointing in a particular direction, and you end up with a stronger magnet, a permanent magnet. So that's how you magnetize iron or cobalt or nickel, is you take it and you put it in an external magnetic field, and all of its domains will line up to create a stronger magnetic field. So that's innately where you get like a bar magnet or a kitchen magnet, things like that.
Okay, so this demo is meant to kind of help you visualize these ferromagnetic materials. So here on the left is an example of some type of material. It's got either iron, cobalt, or nickel in it. And these kind of regions here that have like their arrows are meant to describe domains. And so domains are these regions in the material. We have a bunch of the atoms have unpaired electrons, and all their unpaired electrons they have their spin in the same direction. And so naturally in a ferromagnetic material, you have these regions called domains, but overall the domains are kind of going in random directions. And so there's no net magnetic field associated with this. But if you bring a bar magnet closer, so an external magnetic field, closer to your ferromagnetic material, you have the ability to influence those domains to point in the same direction. And so I can bring my bar magnet closer. And as I bring my bar magnet closer, you can see those domains become influenced and they start to line up with the magnetic field associated with my bar magnet. And you have to bring it pretty close. So notice the domains here on this side don't necessarily align with this bar magnet's magnetic field. But I could reset it, and essentially, even though I reset it, they're going to line back up again. Okay, so as long as you've lined them up, now you can move your bar magnet away and you've created a magnet because now this has a magnetic field in a particular direction. And so you can actually do this with, if you have a magnet at home, you can take like a paper clip or any other type of material that has some type of iron in it, so any kind of steel. So usually like nails, paper clips, and you can place it on top of the bar magnet. And bar magnets magnets at home are pretty weak, so it may take a little while for the domains to line up. But if you left it there overnight, the next morning you would pick up your little piece of metal, and it should be magnetized because you've aligned those domains.
Let's look at this idea of if this is kind of how you form a magnet in terms of how can you destroy a magnet. Well, destroying a magnet essentially is causing these domains to become unaligned. So physically dropping or hitting the magnet will cause the electrons to jostle a bit and they won't line up. If you heat up a magnet, then naturally those molecules will move around and the domains are not going to line up anymore. If you take a magnet and you put it in a magnetic field that is opposite its magnetic field, you'll cause the domains to disalign. So that's why it's important when you're storing magnets to store them properly. Otherwise, you'll weaken the magnetic field. And when we do the lab, we may have cases like that, and I'll have to remagnetize them. So that's kind of with permanent magnets, how you can create, how you can destroy them. Okay? So let's look at just the idea of, we already talked about destroying a magnet. You don't need to write that down, I guess, if you conceptually understand how to destroy a magnet. So don't drop my magnets. Looking at the idea of how magnets interact. Magnets interact with a field. I'm going to turn the projector off. So magnetic force is a field force. It's one of the 3 field forces we studied. Which means that the magnets or the magnetic materials don't actually have to be touching each other. They just have to be within each other's fields. So that's where we're going to really start looking at this idea of a magnetic field and which way it's pointing, etc. So all magnetic materials have what's considered a north pole and a south pole. And a lot of people tend to think erroneously that the North Pole is assigned with a negative charge and the South Pole is assigned with a positive charge, and that's not true. Electrostatics and magnetism are related, but it's not a one-for-one relationship. It's not that you have a North Pole, you're going to have a negative charge. But anytime you have something that is magnetic, it's going to have naturally a North Pole and a South Pole. And we draw magnetic field lines to help us visualize what the magnetic force will do. So magnetic field lines, just like electric field lines, magnetic field lines is a model to help us visualize how magnetic objects will interact. Just like electric field lines. Electric field lines showed us how a positive charge would move if I put it in some other external electric field. The magnetic field line is going to do the same. So with a magnetic field line, the rules for magnetic field lines are that magnetic field lines always point towards the south pole. know it's a little counterintuitive because we always think our compass points to the North Pole, and that's true. The compass points toward the geographic North Pole, but it's actually the magnetic South Pole. And when you come back to class, we'll talk a little bit more about kind of the Earth's magnetic field and kind of the weirdness and the oddities of the Earth's magnetic field. But for our purposes, for physics, you need to understand that magnetic field lines are always going to point towards the South Pole. Just like electric field lines, the density of magnetic field lines tells you the strength of the magnetic field. So if you have a lot of field lines in a given space, then the magnetic field tends to be stronger. If you don't have as many field lines in a given space, then the field is weaker. So that's similar to electrostatics or electric field lines. Just like magnetic field or electric fields, magnetic field lines can combine to become stronger, or they can subtract to become weaker. Add or subtract to change strength. And I think that's all the kind of, so you're going to do a lab on Monday, kind of just playing around with some bar magnets and looking at what's happening to magnetic field lines and how they're adding or subtracting, things like that. One last little thing in terms of magnetic field lines. We will look at the outright equation for some magnetic field lines, but for our purposes right now, the symbol for magnetic field is a capital B. I don't know where it comes from. And the units for magnetic fields are Teslas. In terms of sources of magnetic fields, we talked about permanent magnets. And with permanent magnets, those are those ferromagnetic materials, so iron, cobalt, or nickel, that we put in some external magnetic field and line all those domains up. And the other source are moving charges. So moving charges create magnetic field lines around them, or create basically a North Pole and a South Pole. So moving charges create their own magnetic field. And so we'll look at the equations for how that arises. Okay?